Section: Introduction. In this section, we explore reinforcement learning with verifiable rewards, RLVR, and its surprising effectiveness in improving mathematical reasoning, even when using weak or flawed rewards. We demonstrate that applying RLVR to Qwen 2.5 math models, a well-regarded model family, can lead to significant accuracy gains. For instance, training with incorrect labels yields a 24.1% increase in accuracy on the Math 500 benchmark, while using format or random rewards results in gains of 13.8% and 21.4%, respectively. Notably, these gains from spurious rewards are comparable to the 29.1% improvement seen with ground truth training. We observe similar patterns in more difficult math benchmarks like AMC and AMY. Our findings indicate that we do not fully grasp how RLVR enhances performance. It seems to reveal inherent abilities of the model learned during pre-training, alongside the reward signals it receives. We conduct a thorough experimental study to assess the impact of weak and spurious rewards across different models. For models not specifically trained for mathematical reasoning, such as Olmo and Llama, we notice a significant difference. These models show little to no improvement or even decline when trained with spurious rewards, suggesting that pre-training differences play a role in RLVR outcomes. To clarify this discrepancy, we analyze the reasoning patterns that RLVR tends to favor. We find that many answers from Qwen 2.5 Math 7b on Math 500 involve reasoning expressed in Python, which we term code reasoning, despite the model not executing any code. This code reasoning is a strong predictor of performance, with an accuracy of 60.9% compared to 28.0% without it. We see that both code reasoning and Math 500 accuracy improve consistently during training with any spurious reward, leading to a high frequency of code reasoning after training. Based on this observation, we hypothesize that methods increasing code frequency should also boost test performance. Our experiments support this, as we implement prompt-based and RL-based methods to enhance code reasoning, resulting in significant performance improvements for Qwen 2.5 Math 7b. These results remain robust across different prompt variations, even though the model's initial performance can be sensitive to prompts. We conclude by discussing why spurious rewards can still yield positive results. Our findings raise new questions and have practical implications, highlighting the importance of reasoning patterns established during pre-training on downstream RLVR training. Qwen models, known for their open weights and strong reasoning capabilities, have become the go-to choice for RLVR research in the open-source community. We show that substantial performance improvements can be achieved with Qwen models, even using entirely spurious reward signals, suggesting that future RLVR research should also be validated on other models. We introduce a series of reward functions to replace the standard ground truth reward, including weak rewards like majority vote and format rewards, as well as spurious rewards such as random and incorrect rewards. Remarkably, we find that all these weak and spurious rewards are sufficient for RLVR to significantly enhance the math performance of Qwen 2.5 Math. In our experimental setup, we follow recent RLVR methodologies and use GRPO to fine-tune Qwen 2.5 math models. The standard RLVR approach pairs questions with ground truth labels, providing binary rewards based on the correctness of generated answers. We substitute this ground truth reward with various spurious binary rewards that do not rely on ground truth labels, aiming to explore the minimal supervision needed for effective RLVR training. We train on deep-scale R data with these different rewards while keeping other experimental conditions constant. We evaluate performance using pass at 1 and average at 8 accuracy on standard math reasoning benchmarks, Math 500 and AMC, respectively. Additional results on AMY 2024 and 2025 can be found in the appendix. We adhere to the default evaluation setup in the popular RL framework OpenRLHF, using the official system prompt for Qwen 2.5 Math and no prompts for other models in our main experiments. Further analysis on prompt effects is available in the appendix, where we show that Qwen 2.5 Math 7b is sensitive to prompts, with even irrelevant prompts sometimes leading to high initial performance. Full details of our training and evaluation setup are provided in the appendix. Section Summary. In this section, we demonstrate that reinforcement learning with verifiable rewards, RLVR, can significantly enhance mathematical reasoning in Qwen 2.5 math models, even when using weak or flawed spurious rewards, achieving gains comparable to those from ground truth training. Our findings suggest that the effectiveness of RLVR may be influenced by inherent model capabilities learned during pre-training, particularly highlighting the role of code reasoning in improving performance. Section: Standard to weak to spurious rewards. In this section, we explore various types of rewards in our training process. First, we establish a baseline with ground truth rewards, where we use accurate labels to reward correct answers, setting a high standard for reward quality. Next, we introduce majority vote rewards, where instead of using ground truth labels, we rely on our model's prior responses. We select the most common answer from 64 sampled responses for each prompt, even if these labels are incorrect, to guide our training. We then consider format rewards, which further relax the criteria by rewarding any response that includes at least one non-empty mathematical expression, regardless of whether the answer is correct. This approach encourages adherence to the prompt. Next, we examine random rewards, where we assign rewards randomly based on a fixed probability. This means that responses receive a reward with a certain chance, while others get nothing. We find that even this random approach can lead to performance improvements. Additionally, we test incorrect rewards by deliberately rewarding incorrect answers. We label our training data using majority voting and focus on the subset with incorrect labels, rewarding responses that match these labels during training. Our results show that all reward types, even those designed to be ineffective, significantly improve math performance within the first 50 training steps compared to an untuned baseline. However, we note that the Qwen 2.5 Math 1.5b model shows slower gains with random rewards. Interestingly, performance improvements from spurious rewards are often close to those achieved with ground truth labels. For instance, using incorrect label rewards yields a 24.1% improvement on Math 500, compared to a 29.1% gain from ground truth rewards. Even random rewards provide a 21.4% boost. We observe similar trends in the AMC benchmark, where training with format, incorrect, or random rewards yields gains that approach those from majority voting and ground truth labels. In our appendix, we provide additional results for AIME24 and AME25, showing that format rewards come close to ground truth rewards, while spurious rewards still lead to notable performance gains. Our findings support a hypothesis in the literature suggesting that RLVR does not necessarily teach new reasoning skills but instead activates existing capabilities in the model. We demonstrate that even incorrect or random rewards can lead to performance improvements in Qwen 2.5 math models. Lastly, we investigate whether these reward strategies can be applied to other models beyond the math-focused Qwen 2.5 math. We include general-purpose models and other families, such as Llama 3.1 and Olmo 2, to see if the effectiveness of spurious rewards extends to them. We train these additional models using the same setup and report their performance on Math 500 and AMC, with similar but less consistent trends observed in the AME benchmarks. Section Summary. In this section, we explore various reward strategies for training Qwen 2.5 math models, ranging from ground truth rewards to spurious signals like random and incorrect rewards, all of which surprisingly yield significant performance improvements. Our findings suggest that these rewards may activate latent reasoning capabilities in the models rather than teaching new ones, and we investigate whether these effects generalize to other model families. Section: Spurious rewards can benefit Qwen 2.5 models, but nearly always fail to improve non-Qwen models. In this section, we observe that spurious rewards can help Qwen 2.5 models, but they usually do not enhance the performance of non-Qwen models. From our findings, we can draw two main conclusions. First, models within the same family tend to show similar behaviors. For example, both Qwen 2.5 models improve their performance on math and AMC tests with all types of rewards, including incorrect spurious rewards. In contrast, the Olmo models show little improvement from spurious rewards and only perform significantly better with accurate reward training. We believe this consistent behavior among models in the same family is due to similarities in their pre-training data. Additionally, we notice that smaller models are less likely to gain from spurious rewards, possibly because larger models retain more knowledge from pre-training that these rewards can activate. We will further investigate how these pre-existing behaviors affect RLVR outcomes in the next section. Secondly, we find that reward signals effective for one model family do not always work for others. While spurious and weak rewards lead to consistent improvements in Qwen models, they often fail to produce similar benefits in at least one other model, sometimes resulting in no improvement or even a decline in performance. Overall, our results indicate that Qwen models are particularly resilient to variations in reward strength. We also present additional results for other models that have undergone RL post-training in the appendix, showing minimal improvements across nearly all rewards. We emphasize the importance of testing proposed RLVR reward signals on a variety of models. Many recent RLVR methods for reasoning base their conclusions mainly on improvements seen in Qwen models. For instance, our experiments with recent approaches to test time training and one-shot RL reveal that these methods show a similar trend. They yield strong improvements in Qwen 2.5 models, matching the performance of accurate rewards, but often fail to enhance performance in other model families. We suggest that existing Qwen-focused RLVR research should be validated further on non-Qwen models. Next, we explore why different models trained with the same reward function can yield different results. We hypothesize that these differences stem from the unique reasoning strategies each model learns during pre-training. Some strategies may be easily activated by RLVR, while others may be harder to bring out or may not exist at all. We identify one such strategy, using code to aid in math reasoning, that Qwen math effectively employs, unlike other model families. Our analysis shows strong evidence supporting this hypothesis. We also discuss the origins of our two spurious rewards, incorrect and random rewards. We begin with a case study to understand the differences in behavior between Qwen 2.5 Math 7b and Olmo 2-7b before RL training by examining their reasoning traces in response to the Math 500 test set. We notice a significant difference. Qwen 2.5 Math 7b frequently generates Python code to assist its reasoning, even without a code execution environment, which we refer to as code reasoning. We provide more examples and qualitative analysis of this behavior in the appendix. In contrast, we do not see similar code-assisted reasoning in Olmo 2-7b. Our further analysis suggests that Qwen 2.5 Math 7b maintains accuracy when faced with numerical variations in questions from common math benchmarks, correctly predicting answers even when different numbers are used. The model can also produce complex numerical answers with high precision when predicting code outputs. However, when questions are rephrased with different narratives, the model stops using code reasoning. We believe that Qwen 2.5 Math 7b has encountered many code-assisted math reasoning examples during pre-training. Importantly, the use of code is not just superficial, it strongly predicts answer correctness. We find that Qwen 2.5 Math 7b achieves significantly higher accuracy on math prompts when using code reasoning compared to relying solely on natural language reasoning. Qwen 2.5 Math 1.5b, which was pre-trained on the same data as Qwen 2.5 Math 7b, also demonstrates effective code reasoning. This pattern is not seen in other models, which we categorize as no-code or bad code. No-code models, like Llama models and Olmo 2-7b, do not generate code and thus do not benefit from this reasoning strategy. Bad code models, such as Olmo 2-7b SFT and Qwen 2.5-7b, attempt to use code reasoning frequently, but this often correlates with poorer performance. Therefore, effective code reasoning is a unique capability of the Qwen 2.5 math models before RLVR training. Section Summary. In this section, we observe that spurious rewards enhance the performance of Qwen 2.5 models but not other model families, suggesting that model-specific pre-training influences their response to reward signals. We also identify that Qwen 2.5 Math 7b effectively utilizes code reasoning during problem solving, a strategy absent in other models, which contributes to its superior performance. Section. RLVR with spurious rewards can upweight pre-existing reasoning strategies. In this section, we examine how the reasoning behavior of our models changes during RLVR training by focusing on two key aspects: accuracy on the Math 500 dataset and the frequency of code reasoning, indicated by the use of the term Python in responses. We observe that the rewards we used, including some spurious ones like random and incorrect rewards, significantly improve the accuracy of the Qwen 2.5 Math and Qwen 2.5 models by encouraging the correct reasoning strategies. We track the percentage of Math 500 responses that include Python code before RL training and analyze their accuracy based on whether they contain code or only natural language. Our findings show that Qwen 2.5 Math models perform better when they use code, while other models do not see similar benefits. Notably, some models, like Qwen 2.5 to 1.5b and Olmo 2 to 7b, never generated code at all. We find a strong correlation between performance and the frequency of code reasoning. Before RLVR training, Qwen 2.5 Math 7b shows a high rate of code reasoning solutions, even without explicit prompts to use code. After RLVR training, the frequency of code reasoning rises quickly to around 90% within the first 15 steps, closely linked to improvements in accuracy. Random rewards lead to a slower increase in code frequency, eventually reaching about 65%. We also note that while code reasoning frequency increases with RLVR training on accurate labels, it tends to drop as the model's natural language reasoning accuracy improves, indicating that the model is acquiring genuine knowledge from high-quality rewards. For the bad code models, we see that a decrease in code reasoning frequency aligns with performance gains. We also observe shifts in reasoning strategies during RLVR. Qwen 2.5 Math 7b's accuracy improves by an average of 71 absolute points across various training signals. To analyze this further, we categorize the model's performance based on 4 distinct subsets of test prompts. 1. Code to code. 2. Code to language. 3. Language to code. And 4. Language to language. We focus on the frequency and accuracy of each subset. Our analysis reveals that after RLVR, the model increases its use of code reasoning across all weak and spurious rewards. While few problems that initially used code switch to language reasoning, many problems that started with language reasoning switch to code. The ground truth reward does not follow this trend. For the bad code models, effective rewards help steer them away from poor code reasoning. We find that code reasoning decreases with ground truth, majority vote, and incorrect rewards for Qwen 2.5-7b, but only with ground truth and majority vote for Olmo 2 to 7 BSFT. In contrast, no-code models do not show meaningful changes in reasoning strategy, likely because this capability was not developed during pre-training. Regarding accuracy, we see a significant increase in the language-to-code subset after RLVR across all training signals. This is reflected in our data, showing that 58.3% of the performance gain for Qwen 2.5 Math 7b comes from this subset. Similarly, for Qwen 2.5 Math 1.5b, the switch from natural language reasoning to code reasoning accounts for 78.7% of the performance gain. For the bad code models, the code-to-language subset contributes to 93.9% of the performance gain for Qwen 2.5 to 7b. This makes sense, as the model performs better in language reasoning than in code reasoning, and RLVR training encourages it to use the strategy it excels at. For no-code models, since there is no code reasoning before or after RLVR, all performance changes stem from the language-to-language subset. Overall, these results suggest that much of the accuracy improvement from RLVR on spurious rewards in Qwen 2.5 Math and Qwen 2.5 arises from prompting the model to adopt the correct reasoning strategy. Section Summary. In this section, we analyze the reasoning behavior of models during RLVR training, finding that spurious rewards significantly enhance accuracy by promoting effective reasoning strategies, particularly through increased code reasoning. Our results indicate that models like Qwen 2.5 Math benefit from switching to code reasoning, leading to substantial performance gains, while other models show less improvement due to their inability to generate code. Section. Intervening explicitly on code reasoning frequency. In this section, we investigate how explicitly increasing or decreasing code reasoning affects performance. We have observed that code reasoning frequency rises during RLVR, which is linked to better test results. We aim to determine if boosting code reasoning directly leads to performance changes. If our hypothesis is correct, that more code reasoning significantly contributes to the performance improvements of Qwen 2.5 Math 7b when trained with misleading rewards, then our interventions should lead to noticeable performance changes. We found that encouraging code reasoning enhances the performance of Qwen 2.5 Math models while generally harming other models. We promote more frequent code reasoning through two methods: 1. Prompting, and 2. RLVR training. For prompting, we instruct the models to start their responses with, "Let's solve this using Python." This approach improved the accuracy of Qwen 2.5 Math 1.5b, Qwen 2.5 Math 7b, and Qwen 2.5 to 1.5b by 24.2%, 15.0%, and 10.0%, respectively. However, we noticed a decline in performance for models like Llama and Olmo 2, which aligns with our earlier findings that these models struggle with effective code reasoning. To increase code reasoning through RLVR, we provide a positive reward only when a response includes the word Python, which we call a Python reward. This method proved effective, as Qwen 2.5 Math 7b produced code reasoning solutions in over 99% of its answers after just 20 training steps. We observed performance improvements specifically in the Qwen 2.5 Math models, while other models showed limited gains. Notably, the performance improvements from RLVR matched or exceeded those from prompting. We also explored the effects of inhibiting code reasoning during RLVR with misleading rewards, which can reduce gains for Qwen 2.5 Math 7b but increase gains for other models. We hypothesized that code reasoning contributes to the benefits of weak and misleading rewards. To test this, we created compound rewards that combine each weak or misleading reward with a no Python reward, rewarding responses only if they meet the original condition and do not include Python. Our findings confirmed that these compound rewards did not improve Qwen 2.5 Math 7b when paired with the no-code reward. While the misleading compound reward performed similarly to the original on Math 500, gains persisted but were reduced on tougher benchmarks like AMC and AMY. We suggest that while reducing code reasoning negatively impacts the misleading reward as expected, other positive behaviors may still be triggered. Additionally, ground truth rewards continue to provide benefits, indicating advantages beyond just encouraging code reasoning. Interestingly, for models like Qwen 2.5-7b and Olmo 2-7 BSFT, compound rewards often outperformed the original rewards. Notably, Olmo 2-7 BSFT, which struggled with standalone rewards, improved significantly when the no-code reward was added. We believe this is because these models initially exhibited weak code reasoning, so the compound rewards help downplay less effective behaviors. Next, we discuss our hypotheses regarding how misleading rewards can create valuable training signals in RLVR. For incorrect rewards, we propose two mechanisms. First, many incorrect labels are still close to the correct answers, reinforcing mostly correct reasoning. Second, incorrect labels may act like format rewards, requiring the model to extract and evaluate answers correctly to receive positive reinforcement. Regarding random rewards, one might think they improve Quen 2.5 math performance simply because most rewarded answers are correct. However, since GRPO normalizes rewards to a mean zero distribution, this reasoning is flawed. If most rewarded responses are correct, then most penalized responses are also likely correct. We will demonstrate that our observations about random rewards hold across various probabilities and explain why random rewards can still provide useful training signals despite their randomness. Finally, we will validate our hypotheses through experiments. Section Summary. In this section, we investigate the causal impact of explicitly inducing code reasoning in models, finding that increased code reasoning significantly improves the performance of Quen 2.5 math models while degrading others. We also explore how spurious and random rewards can provide meaningful training signals, suggesting that incorrect rewards can reinforce correct reasoning and that random rewards may still yield useful patterns despite their randomness. Section: Random rewards with varying probabilities consistently improve performance. In this section, we demonstrate that using random rewards with different probabilities consistently enhances performance. We train Quen 2.5 Math 7b using GRPO, assigning random rewards based on specific variables. Each response gets a reward of 1 with a probability of 25% and 0 otherwise. Our results show that all configurations with non-zero probabilities lead to significant performance improvements after an initial exploration phase, achieving results similar to those with ground truth rewards. The configuration with constant rewards does not improve performance, as expected, since it lacks a learning signal. While the speed of convergence varies, all configurations eventually reach high performance levels, with accuracy improvements of 15 to 20 percentage points on Math -500. We note that GRPO's clipping bias can create random reward training signals. GRPO calculates a normalized group relative advantage for gradient updates, and we find that the expected advantage, which influences the direction and size of these updates, is 0. However, due to the clipping mechanism in the loss, the expected gradient is not 0. Following previous findings, we hypothesize that clipping bias enhances high prior behaviors under random rewards, which we confirm by showing that it increases the model's token probabilities for training answers, indicating a greater reliance on prior knowledge. To test the impact of clipping in GRPO, we remove the clipping bias during training by either turning off the clipping term in the loss calculation or adjusting training and rollout batch sizes to avoid triggering clipping constraints. Our findings indicate that, under standard GRPO with clipping, random rewards boost code reasoning behavior, focusing the model on its existing reasoning patterns. This effect disappears when clipping is disabled. While random rewards lead to a performance gain, removing clipping results in no significant improvement. We also observe that training without clipping is unstable, and the model may achieve high performance inconsistently across different runs. We plan to analyze the exact mechanisms behind these observations in future work. Our research shows that GRPO's clipping mechanism can provide valuable training signals, even from noisy rewards. We suggest that the training signal in random reward scenarios may stem from the optimization algorithm's bias towards exploiting learned priors. Other factors beyond clipping might also contribute to model improvements with random rewards, which we will explore later. In the related work section, we discuss various approaches to unsupervised reinforcement learning. For instance, self-consistency preference optimization trains models to favor consistent answers, while test-time reinforcement learning uses majority voting to estimate pseudo-rewards, leading to performance gains in mathematical reasoning tasks. EMPO adapts PPO or GRPO for unsupervised RLVR by calculating rewards based on minimizing query entropy. These methods indicate that internal model consistency can serve as a useful proxy for correctness, although they do not systematically examine how different training rewards impact various model families. In our discussion, we highlight that RLVR with weak or misleading rewards enhances reasoning in Quen 2.5 math models by amplifying existing reasoning patterns. We find that RLVR promotes more frequent code reasoning, which correlates with higher accuracy. Our experiments confirm that both code usage frequency and test accuracy increase during RLVR training across all reward settings for Qwen 2.5 math models. Additionally, we show that directly encouraging code reasoning leads to significant performance improvements. Our findings suggest three key implications. Pre-training of the base model significantly influences RLVR outcomes. Even flawed supervision can enhance reasoning by triggering useful behaviors, and effects observed in one model family may not apply to others. We emphasize the need for testing across multiple models with different pre-training distributions and various baselines when evaluating reinforcement learning techniques.